You curious people of the internet asked me how to rebuild the infamous Windows 95 screensaver called Pipe Dream. So in essence, how to fill a 3D space with splines that only take like 90-degree turns. And the general idea goes like this. You start off with a uniformly spaced apart grid. That means all the points in the grid have the same distance to each other. And we have this grid in 3 dimensions, so also here, same distance between each of those points, like this. And we're always working on one active point. In our case, it's the center point here, the blue point. And from this active point, what we're going to do is we're going to look for the 6 closest points to that point. In our case, those would be those purple points here. As soon as we found those points, we will randomly decide which of those points that we found will be our next point in the line. So we will just roll the dice. And in our case, our next point was randomly chosen to be this. So the next step I'm going to do is I draw a line between my previous point and my next point. And after that, I will set my old point to be inactive, so that as soon as I'm looking for close points on this point, it won't find this old point anymore. And that is the whole algorithm. There is one special case which we have to take care of, and I'm going to go over that case while we implement this. In Houdini, as always, first thing I'm going to do is drop down a GeoNode, dive in, delete our standard file open, and replace it with a box. And the first thing I'm going to do is generate this uniformly scattered grid. And the way I'm going to do it is with a VDB. So just going to create a VDB from polygons first. And I want this VDB to be a fog VDB, so it stores a density value. And I'm going to dial down the voxel size a bit to say something like 0.01. Next thing I want to do is drop down a volume bop and make sure the density attribute is uniformly set to 1, just by simply going in there and wiring up a constant set to be 1 into the density output here. And the next node is going to be crucial for our uniformly scattered grid, and it's the points from volume. And this sub creates exactly what we need. A uniformly scattered grid of points, and it has 2 modes. On the one hand, this grid layout, on the other hand, a tetrahedral layout, which is helpful when you're dealing with tetrahedral and hexagonal grids. In our case, let's just leave it to be a grid and maybe dial down the point separation a bit so it's spaced 0.05 units apart, like so. Now that we got our grid, the first thing I want to do is create a group which stores which of those points has already been turned into a line, so which of those points is already part of a spline that we are drawing, and which of these points is still free for our algorithm. So let's do that with the help of a point wrangle. Wire this up, and within the point wrangle we're gonna create our group with the help of the setPointGroup function. And we want to operate on our 0 input slot. And let's call our newly created group food. So the points are kind of the food that our algorithm consumes. And our current point should be in that group. And the point wrangle will automatically execute this for all of the points. So let's highlight it, go into the geo spreadsheet and check. Yes, each one of our points is in the food group. Next thing I want to do is set up my starting points, so the points from which my algorithm will start. I'm going to do that with a point wrangle again. And this time I will set it up so that it only runs once. I'm going to go to run over and select detail only once. And within this point wrangle, I want to be able to set a given number of points, which we're going to choose randomly as our starting points. So I'm going to drop down a for loop first. And I want my variable to be 0 first. And want to run this, let's say, 10 times for the beginning. So what this expression tells Houdini is run this loop 10 times and increase my variable I by 1 for each run. So now within the loop, let's create another variable called PTID for point ID, and it should be an integer, and it should be a random integer. And as the random seed, we're just going to use RI. And what this random number should be is it should be a random point number. So it should range from 0 to the maximum number of points in my grid here. And I will assure that by multiplying this value, which will range between 0 and 1. I will multiply it by my number of points, called numpt. So this expression will yield a random number between 0 and my maximum number of points. So it will randomly choose one of the points. And with that randomly chosen point, I want to put that in another group. Again, let's use the setPointGroup function here. And the group I want to put that point in will be called active. This is the group's point ID that we just generated randomly. And this tells it to be in the group. Also, I would like to tell this point to not be in the food group anymore, like so that it can only be either active or in the food group. Okay, let's highlight this, go into the gear spreadsheet, and that somehow did not work. Just needed a refresh, so it's actually working. We have our 10 active points here, and they have a pretty random numbers selected here, and they are not in our food group again, and vice versa. Perfect. Now let's work on our algorithm by dropping down another point wrangle. And remember, now we're all set up to perform this algorithm that I've been talking about in the intro. So let's first define a few variables. On the one hand, an integer called maxpt for max points. In our case, it should be set to 6. And a float called maxRadius, maxrad. And let's set this to be a little bit higher than our point spacing in the points from volume. So this is set to 0.05. So let's set our maxrad to 0.06. The next thing I want to check in the point wrangle is, as it's running through all of the points, I only want to execute the code in the point wrangle for a point that is in the group active. So let's check that with the help of an if statement. And we can do that quickly with this syntax: if add group underscore and then the group's name, in our case active, equals exactly 1. Then run through this code that's in those curly brackets. This is a neat abbreviation for checking if a point is in a group or not. So if you write down add group underscore and then the group's name, Houdini is going to evaluate if that point is in the group and it will return 1, or if that point is not in the group and it'll return 0. So let's first find some close points with the help of our pgfind function, which again is an accelerated version of the pcfind. And we need to tell it to look for points on input 0. And we only want to find points that are still in the food group. We want to search from our current point's position within the max radius. And we want to find a maximum number of max PT points. And the pgfind needs another parameter for its acceleration structure. And as long as we're searching within a radius that is not changing that much, we can just give it that max radius again. Like so. And we want to write those found points into an array, into an integer array, and let's call it close PT for close points. Next thing I'd like to know is how many points we actually found. So in order to check for that, I'm just going to create another variable called number of close points, and let's call that close points, not close point. And the number of close points is equal to the length of that array, like so. So now that I've found those 6 closest points to my active point, I need to randomly choose one of those points. Let's do that by creating an integer. Let's call it direction. And it's going to be an integer of a random number. And as a seed, let's take the current point ID. And to adjust it a bit, let's create a slider, an integer slider, chi, and call this one seed and add it to the current point ID. Let's just click this create spare parameter button here, and Houdini automatically creates a slider with an integer where I can choose a seed. But what this still will yield is a number ranging from 0 to 1. So when I turn that into an integer, it's going to be either 0 or 1. To fix that, let's multiply my random number before it gets cast to an integer with our number of close points, so with the length of our array here, so that I now get a random number between 0 and the maximum number of close points there are. Okay, now let's talk about the special case that I mentioned in the intro. Our current implementation, if we just continue without checking for one condition, will work only in a part of the cases, because there could be cases in which our active point is not surrounded by unconsumed points in its vicinity. So it will not find anything. So we need to check for this case with an if statement. And we check if the number of close points is greater than 0. So if we actually found close points up here. And if we actually found close points, let's get the ID of the point that we randomly selected by creating another integer called point ID. And this is going to be the index direction in our close points array. So we randomly generated this index here, and it's going to be in the range from 0 to our maximum number of found points, and we randomly select one of the elements that's stored in the close points list here. Let's use this point ID to create a line between those 2 points by first creating a new primitive, a new polyline. And then adding the 2 points that we have, our currently active point and the newly found point, as vertices to this new primitive. So this adds my currently active point. Let's copy that, paste it here, and we'll add the found point. What we have to do now is set our groups accordingly. So let's first set our newly found point to active. So our newly found point is now within the point group active. And let's copy that and paste it down here. And let's set our previously active point that we're still working on to be inactive now. And we also have to make sure that both our newly found point and the point we've been working from are not members of the food group anymore. So let's do that again by using this expression and just setting both points to be not in the food group anymore. Like this. This is the case in this if statement if we actually found close points. However, we need to take care also of the case that we actually did not find points. Let's take that case into account by dropping down an else. So if we didn't find any points, let's execute the code that's within those curly brackets here. And if we did not find any point that we can jump to, let's just search for any other point that is left in the point array that we could use to draw another spline. And we're going to do that by creating a variable called new point ID. And we will just look for a nearest point to our currently active point that is in the food group. So we're working on the 0 input slot. We want to search in the food group and from our current point's position. And this does not have any restriction on the radius it searches. So it will search through the whole point group food and find any point that is left and jump to this point. So if we found a point like that, let's not draw a line because that would yield a jumpy line just going randomly through our point grid, but instead just set those groups here. So we just copy this, paste it in here, and let's adjust our variable here. It's called nptid. For new point ID. Okay, like so. And this is our algorithm. Let's take that and drop down a solver. Wire this in here, cut that, dive in the solver, paste our point triangle, wire this up, head up one level, highlight it, and as with most algorithms, if I just hit play, we see it works, but we still have those points here. So after my solver, let's drop down a delete node. and delete all points that are in the food group. Set it to delete points and delete selected. Okay, now we got rid of the points, and if we hit play again, we can see that our space is filling with those right-angled curves. The nice thing about this setup is, as I'm using the VDB from Polygons node here, that I can wire in basically any geometry up here. So it doesn't need to be a box. I could use a random geometry like the trusty old rubber toy and have lines grow through that. Or I could use any geometry that I like to generate really intricate patterns that form the outline of the bounding geometry. So, as always, I hope you're having fun with this algorithm. If you create any artwork that you'd like to share, please tag us, please send us a message, please send us a link. We're really eager to see what you guys come up with. And it's cheers and goodbye.